Okay, so once again, I guess I'll keep talking. So thank you guys very much for showing up for this presentation. I will go over really quick. Some of the concepts I've already sort of glossed over during my previous talk, but we'll talk about some of the technology and the core innovations of the Taraxa protocol. We're still very much a work in progress. So I really want to have the opportunity to discuss some of the technical details and the innovations with everyone sitting here. So okay, so we'll go through this is the agenda for today, and we'll do a quick introduction. So we were founded in 2018, and we're based in Silicon Valley. Our office used to be in Mountain View. We just moved like yesterday to Santa Clara, much better space. Also right next to places like Analog Devices and AMD. So hopefully I'll just stand in front of the door and say blockchain insert in your chip. Right? Pretty interesting. So there's several design goals when we first built Taraxa. I mean, when I first set it out to think about entering the blockchain space, we actually just wanted to build applications. But because the underlying protocol seemed, very immature at the time, this was back early 2018, late 2017, we thought that actually for any application team to be successful in the blockchain space, you actually still need to have the capability to design and adapt the underlying protocol, right? It's either doing that or wait 10 years before the the protocol space becomes mature. So of course we actually built it to scale to enable device independence and actually also to self-evolve. So here are some of the innovations that we're introducing. The first one we talked about, we're introducing speculative concurrency into individual nodes to allow parallel execution because everything right now is executed sequentially on blockchain nodes. The second one is, we also talked a little bit about that. We're using a block DAG topology, but at the same time we're offering a rapidly finalized topology to actually give finalization to smart contracts and high-value transactions. Lots of feedback. The third one is what we call fuzzy sharding, which is also something I mentioned before. We need ways, if we're not using proof of work, for example, we need ways to limit block generation and actually define transaction jurisdiction, right? How do you know which transactions are you allowed specifically to pack into a block? Or else everyone's just going to pack out the exact same block and you have complete overlap and wasted work, right? The next one is that we're very interested in building trustless light nodes. So most light nodes today, or pretty much all light nodes today, they latch onto a specific device, like a phone node, right? So in Ethereum or in BTC, they're called SPV-enabled phone nodes that actually respond to light node requests. These light nodes are actually, they can be tricked by the phone nodes, right? So the phone node, of course, sends back, in Ethereum, they send back a Merkle proof. So, that's not nothing, but it's still fakeable, right? So for light devices, we want to make sure that despite the fact that they don't have enough resources to conduct independent verification, they're still not easily tricked. So we're going to set up a layer of service that allows the light node to pull a random subset of the network to actually verify whether or not what's being told is true. And the last one is the idea of an evolving network. I think most new blockchains that are coming out realize that the existing governance model, right, for very simple things, right, like technical parameters, like how big is the block, 1 megabyte or 2 megabyte, or what is the difficulty level, et cetera, et cetera. So a lot of these questions are being today decided on Reddit forums. They're being argued in offline meetups, and people argue about them 2-3 years, and nothing gets done, right? So it's not the best way to govern a protocol. We already have a consensus network. I think it's very easy to actually build out very simple machine learning algorithms to study past network behavior and decide what the right parameters are or should be for the next iteration of the network, right? For example, if for the past 3 periods, we see a very high volume of transactions. Well, maybe now it's time to actually bring more block proposers, right? And actually more finely divide the transactional jurisdiction so that we have higher throughput. If there's been no transactions in the past, 3 periods, well, then it doesn't make sense to have all those block proposers because they're just going to, propose the exact same thing. So maybe we lower the number and lower the number of transaction jurisdictions, right? So there are a lot of these decisions that can be made on the fly So today's talk, right, we're mostly going to focus on these scalability solutions. Okay. So we're going to look at things like horizontal and vertical concurrency, right? Their motivation, how we implemented it, and then I'll just give you verbally some very empirical results, right? Very preliminary, so don't hold my word to it. Okay, so the first thing I want to talk about is that what is concurrency, right? So everyone talks about things like sharding and horizontal concurrency, but what exactly is concurrency? So everything when they're executing sequence, right? They're just one after the other, one after the other. They're sequentially executed, right? When you have horizontal concurrency, then what you have basically is that, well, here are a bunch of tasks that's just divided into 5 pieces, right? And then give these 5 pieces to 5 groups of people, and they're going to work on it, in parallel, right? That's horizontal concurrency. So these 5 people will just do one after the other, and they do it 5 at a time, right? So that's horizontal concurrency. Sharding solves this problem, right? So the question that we look at is, well, why are they processing it 1 at a time, right? So why can people within these 5 groups, why can they process it 3 at a time, right? Doesn't that go much faster, right? So this is what we call vertical plus horizontal concurrency. So these are the things that we're looking at, okay? So we talk about this 1 at a time. So let's talk about horizontal concurrency. This wireless is broken. So I was trained as an RF engineer, actually. So once you're an RF engineer, you actually look at wireless communication as magic. Electric fields, magnetic fields, it's magic. No one knows how it works. So we actually talked about this before, is that actually single chain topology, as we see in Bitcoin and Ethereum, they have very, very tough trade-offs, right? I mean, these are just not things that you can bypass, right? We talked about, hey, what if you speed it up by making the blocks really big? Well, if you make the blocks really big, then they propagate very slowly through the network, and everyone sees a different version of the network because the blocks come very slowly, and then you end up with a lot more branching, right? And branching for single chain topologies like Bitcoin and Ethereum is very, very bad, right? You end up with a lot more branching, people betting on the wrong chain, people have different views of the network, then you have to end up waiting longer for the network to converge. So you actually don't get any speed up, right? So that's not great. And then the other one is the block generation rate. What if you just, instead of very large blocks, what if you just have lots of little blocks, right? Well, if you have lots of little blocks, once again, the network becomes inundated with lots of little blocks, and then everyone has a lot more choices, right? Instead of just choosing between 1 or 2 blocks, now they have choices between 10 different blocks, right? And since only 1 block can win at any given time, there still increases the odds of you betting incorrectly, and also increases branching, right? And once you increase branching, once again, that sacrifices security, you end up having to wait longer for convergence. So this is sort of just like a no-win scenario, right? You just can't win, right? And what are you going to do about it, right? What are you going to do about it? Well, what if you had a more inclusive technique where multiple blocks can be, I'm studying too much feedback, huh? Okay. Where's the speaker? Okay. This place is good? All right. Oh, there's live stream. Okay, yeah, they can't hear me. So what's very interesting about a block DAG topology, right? So there are several characteristics. First of all, each block, they point to multiple parents, right? They point to not just a single parent, like in single chain topologies. They actually point to multiple parents. So when you're proposing a block, what you're supposed to do is that you're supposed to look at the frontier of the graph, right? You look at the frontier of the graph, and then you point to every single block that you see at the frontier of the graph that you believe is legitimate, right? So these pointers, right? They're very interesting, right? So these pointers they do several interesting. They have several interesting properties. The first thing is that they actually establish order, right? Partial order. What does partial order mean, right? Say like This block is pointing to this block. Guess which one came first? This one, right? Because it had to have known this one to point to it, right? So right away, we have order between these two blocks. So it's order. The second thing that it does is voting, right? What does voting mean? Well, it means that when I'm building this block, when this block is being built, it sees these two blocks, and it believes that those two blocks are legitimate, right? So what's embedded inside these blocks are now these implicit votes, right? This is very, very interesting. And these votes later on will be used by the Ghost protocol to actually calculate weights, right? So in a block DAG, you have many blocks that are being proposed simultaneously, and the entire network can actually accept all of them simultaneously. Okay, so so that sounds great, right? Like, did we just get free lunch here, right? So nothing is free in engineering. So if you have multiple blocks all pointing to each other and in a graph, the problem that you run into is ordering. So in any sort of graph topology, right? If you go read any white paper that have graph topologies, they're going to spend a very, very large section of their white paper talking about ordering, right? So how do you order the blocks when you have this big mess of graphs, right? So there are several interesting things here. So the first interesting thing is that we actually make sure that not all the pointers are equal, right? Not all the pointers are equal. So when each block is being proposed and they're pointing to multiple blocks that they see, they have to pick out like their favorite block. Okay, how do you pick out the favorite block? It's the heaviest block amongst the tips that you're selecting, right? So how do you calculate the heaviest block? Well, each block's weight is actually its own weight. For example, this block's weight, let's just use this block. This block has its own weight of 1, and then you see how many blocks are pointing into it. Well, there's one block pointing into it. This block has a weight of 1. So then this block has a weight of 2, right? And then you just, for all the blocks, you recursively go in and you calculate all the weights. Okay, you calculate all the weights. So actually, maybe I should go to some of the later slides to give you guys a better idea. So sorry. Okay. There might be some calculation errors here. So the first thing you do is that you calculate weights for all these blocks, right? You just add them together, right? So for example, 147 is 60 plus 86 plus 1, right? So you calculate all the weights, okay? So the next thing you do is that you can actually find the heaviest blocks, right? You can actually every single time you walk forward, right? Let's start from the genesis block and you walk forward, you pick the heaviest block, right? So this one you go forward, it's like 291, 291, 584, well you go to 584. And the next one you have these choices, 151, 143, 290, you go to 290. And you keep walking, right? So this actually gives you a chain, right? Within the DAG. So if you're happen to propose a block, if I'm proposing this block, right? And I'm pointing to these two blocks that I see that I think are legitimate, well then this pointer here is going to be my special pointer because this is the heaviest tip, right? This is the heaviest tip. It's where the heavy chain in the middle terminates, okay? Everyone still with me? Okay. And then later on, what you can do is that you can actually establish absolute ordering by just following the chain, right? So every block on the heaviest chain, right? On the heaviest chain has their own little like fan club, right? So you have you move from this one to this one. Is this block pointing to anyone else other than the block you're traveling from? No. So it's just by itself. This is its own sort of little fan club, right? Its own little group. You move on to the next one, this 290 block is pointing to these two blocks, right? So these three blocks are its own group, right? And then you go to the next one, 147, it sees this block, so these two blocks are its own group. 86, it sees this block, which also sees this block, so these three are its own group, right? So you group them, right, as you move down the chain, right? And then you find ordering, right? So this is 1, this is 2, you know, and then this is not 3, right? Because these two came before it. It's pointing to them, right? It's pointing to them, so that means these two definitely came before that one. But who is 3, right? These two are the same weight. Well, you use the tiebreaker. For example, the lowest hash wins, right? Let's say this one has a lower hash. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So you just keep on going, right? So that's how you get absolute ordering. Sorry, let me just go back to my previous slides. Okay, yeah. So so you actually can do deterministic ordering, right, throughout this entire thing. But there's another problem, right? There's another problem, which is that this ordering, this can change, right, depending on what type of blocks come after, or whether or not someone's trying to attack a specific block, for example, right? So maybe you see this version, someone else sees a different version. You know, 3 seconds later, this entire thing changes, and this chain, instead of going this way, is now going this way, and it keeps on changing, right? That's not very good. That's where you get the probabilistic finality, right? Okay, so here's what we do, right? In order to introduce some true finality into this network, right? And we said before, it's very important for things like smart contracts. We have another asynchronous process running in parallel. So what it would do is that it would just take a vote, right? It would take a vote and say, you know, let's just vote on a specific block to have infinite weight, for example. Let's put infinity weight on one of these blocks, right? So the Genesis block is not that interesting, but let's just vote on this one and say, now this block has infinite weight, okay? So what happens between blocks that have infinite weight is that the entire group of blocks between two blocks with infinite weight have absolutely finalized order, right? So once you finalize one block here, you finalize everything here, right? They're all finalized, right? So this is a very, very elegant way of finalizing. You don't need to finalize the order of every single block. All you need to do is finalize one block periodically, and then you get deterministic order for the entire period, right? Very, very cool. And the fact that this is happening asynchronously means that it doesn't actually impact any of this stuff, right? So this is actually very, very cool. So this voting process is actually a VRF-enabled subcommittee selection voting process. So this is something that actually was originally proposed by Algorand. So I don't know if you guys have heard of Algorand, but Professor McCaldy came up with this verifiable random function, which is a very, very uniformly, randomly distributed hash function that he had, that also simultaneously produced a proof of the randomness, right? So it uses that to select a randomized subcommittee to actually vote on which block that you're supposed to finalize, okay? Okay, so now we have more problems, right? There are lots of problems to solve, right? So the next problem to solve is, well, you know, if you don't have proof of work, right? So proof of work is a very, very interesting algorithm. It's very simple. We solve a very difficult puzzle. It's also a random number generator. It's also a timer, right? So it's a lot of different things all rolled into a single simple algorithm. It just so happens that algorithm is very wasteful, right? So if we don't use proof of work, then what are we going to use, right? We have to reproduce a lot of the functionalities within proof of work. So the first one that you're supposed to reproduce is who gets to propose blocks. Right? We can't just let everyone propose blocks whenever they feel like it, because then there are too many blocks, right? So so what we do is that once again we run a cryptographic lottery, right? So you can think of every single block in the previous 1.x period, right, including your current unfinalized period, plus all the blocks in the previous period. Every single block you can look at as a lottery ticket. That's your lottery ticket, right? You sign it, you take the hash of it. If that's under a certain threshold, congratulations, you just won. You now have a winning lottery ticket. And this is a purely randomized process, locally computed, right, on your own machine. You don't need to coordinate with anybody else. So no coordination required, okay? And if you have a winning ticket, that means you now have you can propose one block, right? Every winning ticket you have, you get to propose one block. These tickets expire, right, after 2 periods. So you don't get to just keep accumulating tickets and release a ton of blocks all at once, okay? So great, now we have effectively limited how many blocks gets generated on the network, right? So you also have the problem, let's say that we say only 10 out of 10,000 people get to propose blocks. Well, those 10 people, they might just propose the same blocks. Why? Because they might see the same mempool, right? The same set of pending transactions. So they're just going to put all those transactions into the block. So you still haven't solved the problem. Now you have 10 people where 9 people have just wasted their work, right? So what are you going to do then? Well, then only every one of those 10 people, they're only actually able to pack in a subset of the transactions that's actually in the pending queue, right? So once again, this is also done through a similar process. So what you do here is that you take the previous finalized period block, okay, and then you take the sign it, you take the hash of it, and you get a hash, right? You take the hash and you modulo the hash number modulo the number of jurisdictions, and you get a remainder, right? And then you take the hashes that are in this the transaction hashes that are inside the queue, and you take the same modulo of the number of jurisdictions, and you also get a remainder, right? For all the hashes, for all the transactions that end up with the same remainder as the one that you calculated from the period block, those are the ones you get to pack into your block. All the other ones, you don't get to pack into your block, right? Very, very simple. So what you want is that you want the expected value of the number of block proposers multiplied by the number of jurisdictions to roughly equal to 1. In reality, you might want that to be bigger than 1, because what if some of these guys were eligible, they're shut down or whatever. There are also financial incentives you can actually give to make sure that, if you're actually holding on to a winning ticket, but the number of people that, there are also financial incentives, obviously, you give to people to propose these blocks so that, they have an incentive not to be offline, right? So this is how you're supposed to limit block generation and transaction jurisdiction without proof of work, okay? And also without coordination. That's very important. Coordination is very wasteful, okay? Okay, so we've just begun testing. So I'm going to throw out some numbers. These are not going to be finalized numbers. So in terms of transaction per second, I think we're seeing anywhere between 2,000 to 6,000 transactions per second. In terms of network diameter, which is how fast a specific transaction propagates through the network, we're seeing anywhere between 1 to 5 seconds. I think there's actually a lot of improvement we can make here. Block efficiency can be pretty high if we set that to fixed to be the number of proposers, but we still need to develop an algorithm which dynamically adjusts the two. Okay. Okay, so then let's talk about vertical concurrency, right? So this is actually a much simpler concept, but actually much harder to implement than the actual ledger. So why are we looking at vertical concurrency, right? This is a stupid problem nobody looks at, right? So, well, first of all, we think that it's just actually pretty stupid that everything's processed sequentially. Like, why is everything processed sequentially? We all have multi-core processors. It's kind of dumb. And you look at any kind of node, their CPU is not fully loaded 100%, right? And so another interesting fact, this is very interesting. So what we did is that we actually took a random sample of Ethereum transactions from the historical Ethereum from Ethereum history. We took a random sample of 135,000 blocks, and we calculated how long it took to on average to process one transaction. Now we're not making a, we're not distinguishing between coin transactions versus smart contract transactions, right? So on average, it took, unless this result is very wrong, right? It took 10 milliseconds to process one transaction, right? What is 1 divided by 10 milliseconds? That's 100 TPS, right? That's not great, right? I mean, you cannot go too much faster than this because that's how fast they process transactions, right? And someone else might raise their hand, no, some of this is done asynchronously. Okay, fine, let's say 50% of it is done asynchronously. You still only get 200 TPS, right? So another interesting thing about, there are a lot of dirty little secrets within our blockchain community is that whenever someone tells you about their transaction per second, it's guaranteed they're not talking about smart contracts. Okay, they're talking about coins, only coins. Okay, because you're not gonna get over this barrier over here. Maybe you have a faster virtual machine, maybe you have a faster whatever. These things are still significantly slower. Smart contracts are significantly slower, take longer to process than coin transactions, right? So people often talk about there are tons of bottlenecks. There are network latency bottlenecks. There are hard drive input-output bottlenecks. In our case, we're looking at the execution bottleneck. Right? Okay. So there are many layers, right, to actually solve this problem. There are many layers to solving this problem. The first layer, the first iteration, is actually very simple. So what we're going to do is that we're going to borrow some principles from software transactional memory. And do something called speculative concurrency, right? What speculative concurrency means is that, the implication is that the developers does not need to change their behavior. They can just continue to write whatever code that they want to write, and then we automatically insert concurrency at runtime, right? So transactional memory is actually something that was invented by our advisor, Professor Morris Herlihy, back in the late 80s and early 90s, right? Where he pioneered some of the fundamental theories that enable multiprocessor computations, right? So his theories basically was ignored for 20, 30 years, right? So the reason why it was ignored is because during that time, we had Moore's law, right? Moore's law kept going up every single year, right? It kept doubling speed until around 2010, 2011, when Moore's law stopped, right? When that happened, all the chip makers became very nervous. They're like, well, crap, we can't sell any more new chips. So let's talk about multiprocessor computation. So what speculative concurrency is, right? It's actually very, very simple. All we're doing is that we take, for example, all the transactions inside a block, and we just execute them in parallel, right? And then at the same time, on the side, we have a conflict detector, right? So we detect conflicts. The data structure is a concurrent hash table. It detects conflicts, and then if it sees conflicting transactions, that are basically write into the same memory space, it terminates these transactions, rolls back the changes they're making into the persistent state, and then resequences them for sequential transaction. So at the end of every single block, we actually turn this block into 2 sets. We have a concurrent set, and we have a sequential set, right? The concurrent set can be executed in parallel with no problem, and we have the sequential set, right? That must be executing in sequence after the concurrent set. Okay, so this is a highly simplified implementation of software transactional memory. This is the first pass. The results from the first pass are not ideal. We were still working out the kinks, but I think right now we're seeing a roughly 2x improvement. Not great, but it's not nothing, right? So this is the first pass, okay? So if you're paying attention, this is the EVM, right, or the virtual machine. It's not just about execution and reading. It's also about writing, right? So inside the EVM, there are these things called tri-databases, basically a Merkle tree that holds the entire world state, right? And once again, this is sequentially written, also sort of silly. Someone will tell you, well, no, I mean, these are all independent. These are all dependent, right? You have to run them in sequence. Well, not really, because the leaves at every single layer of the tri database or every single layer of the Merkle tree, all the transactions can be done in parallel. Okay, they're guaranteed to be non-conflicting. Okay, it's that every single layer above it, each layer you need to actually do them in sequence, right? There's no parallelization between layers, but on every single layer it can be perfectly parallel, right? So there's actually a lot of room for concurrency there as well. What's also very interesting about our topology is that when you're packing blocks, right? So when you're packing blocks, you're actually not executing anything. And this is actually very key. Typically speaking, right, in typical blockchains, you propose a block, you put the transaction in, you validate it, you process it, and then you throw it out, right? So all these steps are actually locked into the same single step. They're not split apart, right? In our topology, the DAG at the top, it just grows without anything being executed. It just keeps on growing, right? It just keeps on growing. First, then comes finalization, and then comes execution, right? And then comes execution, okay? So there are several interesting things I want to point out here, right? So going back to this try commits, right? The commitment to the try database. Notice that you actually have to make a very similar number of try commits at the upper layers of the Merkle tree. I'm really sorry, I was too lazy to draw the Merkle tree. It's kind of complicated to draw. But anyway, at the upper layer of the Merkle tree, it doesn't matter if you're making one change to the leaves or 2,000 changes to the leaves. You still have to calculate them all the way to the top, right? So if you're calculating them every single time you're packing a block versus calculating them every, say, 30 blocks, right? There's a huge difference in how much time you actually spend writing into the database, okay? So right there's a huge time saving that you actually get from infrequently committing into the database, okay? The second thing I want to point out is that notice that there are two blocks on the finalization chain, right? One block is to finalize a specific block within the DAG to finalize that block, right? The other one is what we call a concurrent schedule, right? So what the heck is a concurrent schedule, right? So remember when we said that we are actually dividing a block into a concurrent set and a sequential set. That is scheduling, right? What's really weird about concurrency is that if I give you a block and I give a block and we execute the exact same block, right? We might actually end up with different schedules, right? Because transactional memory, the way that the CPU schedules these things is actually non-deterministic, okay? So in blockchain, if you have different ordering, you might end up with different results, right? So that's not good. So that's why, in addition to agreeing on which block is finalized, we also have to agree on the concurrent schedules for all the blocks within the period. Okay, so that's also another voting process. We're in a process of actually calculating how long it takes to actually perform this concurrent schedule calculation. If it's sufficiently short in that it's much less than the overall network latency involved in the voting process, we might just merge these two blocks together so that you have a single vote, okay? The third thing that's very, very interesting, and we actually designed it this way, one of the huge benefits of actually having decoupled this portion where you're including transactions into the block away from finalization and execution is that, remember I talked about application-specific ledger design, okay? So we think that a huge, huge subclass of applications for IoT devices is what we call IoT data anchoring, right? You're actually hashing the data you're collecting, signing it, and then throwing it out into the blockchain. That is a very interesting transaction. It's what we call a stateless transaction, right? What does a stateless transaction mean? That means this transaction does not depend on any previous transactions, and it does not impact any subsequent transactions, right? Or it shouldn't impact any subsequent transactions as far as the device is concerned, okay? So by decoupling transaction inclusion away from finalization and execution, these very light IoT devices are able to get just the inclusion confirmation As long as their transaction is included, it doesn't care what order it's executed in because it's stateless. So it doesn't care about finalization, and it doesn't care about this concurrent schedule. It doesn't care about any of this ordering stuff that's happening at the bottom. It just cares that it made it into the block, and that's it. That's all it cares about. Who else cares about this, right? If you're not an IoT device. So I went to a convenience store and I bought like a lollipop. I like lollipops, right? For like 10 cents, right? Do I really care? Like, what is the probability of someone specifically attacking me to screw me out of these 10 cents? Not very likely, right? And if they did screw me out of 10 cents, I don't really care that much, right? So maybe for these extremely small transactions, I don't really have to wait for all this stuff. All I need to know is what's included, and I'm done. I don't really care that much, right? So there are a lot of interesting properties here for, for stateless transactions, for extremely low value things that people just don't really care about. Hey, actually a block inclusion signal is good enough, right? And this is set up exactly to provide that signal, okay? Okay, so so the way that we've been testing this, like I said, vertical concurrency actually turns out to be a lot harder than horizontal concurrency. So the way that we're testing this right now is that because we're using speculative concurrency without expecting the developer to change your code, we're actually testing everything on historical Ethereum blocks. We're just taking Ethereum's history and then we are retracing it, right? And into our concurrent VM just to see how much speed up we're getting, right? So one of the primary barriers to speeding up when we're using a speculative concurrency is contention or conflicts that happen within the transactions, between the transactions within specific blocks. So actually the second thing is new transaction grouping, right? So if I were incentivized as a block proposer to group transactions I believe will not conflict with each other, right? Then we probably get a much bigger speed up. Now people, you might ask, well, how do they know, right, that it's not going to conflict with each other? These are Turing complete languages, right? Well, a very simple first order test is that there are no overlapping accounts that happened within the calls of these transactions. So you can actually regroup them to minimize contention. And the third one is actually much harder because it actually requires developers to change their coding behavior, in which we actually provide what we call concurrent objects, right? So what concurrent objects are is that there are specific data structures written so that the virtual machine has a semantic understanding, right, of what exactly this data is doing. Without semantic understanding, the virtual machine has no idea what these numbers are, right? 2H is a bunch of opcodes, +1, -1. It has no idea what exactly is happening. One very interesting object is a counter, right? We often use a lot of counters, right? So if you actually look at, CryptoKitties, this is what broke Ethereum back in 2018 and 2017, right? So if you look at CryptoKitties, over 95% of all the function calls are occupied by 3 specific functions. 50% of the function calls are called by trading cats. So I'm trading a cat with you, right? We're all speculating on cats. That's 50%. That's perfectly concurrent, right? We actually went into the smart contract. There are no conflicts, right? Because it's very, very rare for multiple people to be trading the exact same cat. It actually doesn't really happen, right? So that's perfectly concurrent. So 50% of that is concurrent, it can be concurrently executed. Now, the other 45% or so are by 2 other functions, right? One is breeding, and the other one is birth, okay? You're breeding different cats, and they're giving birth. Now, looking at the code, those 2 contracts are also non-conflicting, really. But they have this really stupid thing in there. Well, I can't say it's stupid, because I don't know what it actually does. They have a number of pregnant cats as a counter. I have no idea why they have that counter. I need to go back and look at a contract. But that counter guarantees a conflict because it's a global variable that gets touched every single time you execute a contract. No matter which 2 cats are getting pregnant or which 2 cats are having birth, right? That counter is getting hit. Well, if you have a concurrent object, for example, if you say, hey, if you're going to use a counter, use a Taraxa concurrent counter, and you just put that into your code. So what the virtual machine knows is that, hey, actually, this is a counter. It doesn't matter what order I actually run it in, because counters are counters. They're monotonically increasing, right? It doesn't really matter. So I'm just gonna run that part of it in sequence, right? And the rest of it can be in parallel, right? So of course, you gain a lot more concurrency by making the virtual machine a lot smarter, basically by getting the programmer to give the virtual machine some interesting information, right? So one interesting experiment that we're going to do is actually write a concurrent version of the CryptoKitties and see if it coughs up the network again. We don't think it will. It'll be pretty interesting. Okay, so those are some of our scalability solutions. And some of the target applications, we talked about how IoT infrastructure, we believe that devices are much better suited, right, for blockchain or for decentralized transactions and identities than human society is. We think blockchain actually gives devices very interesting properties, right? It gives them unique identities, right? Right now, devices are nobody, right? My phone only knows, I know what my phone is. Apple knows what my phone is. Some other apps know what my phone is, but normally other people don't really interact directly with my phone, right? They interact with other companies or other people. So this gives devices unique identities. It gives devices the ability to own assets, right, and actually make economic decisions. And it also gives devices a lot more independence and self-governance, right? When the number of autonomous devices scale up exponentially, it's non-scalable and also very insecure to start governing them, in a centralized manner. So they have to start making decisions on their own. Okay, so some of the interesting applications that we're working on, right? I think I've already talked about the data anchoring example where we work on the bridges, right? The infrastructure. Another thing that we're very interested in enabling is actually having manufacturers provide a decentralized certificate authority for their devices, so that these devices are actually able to trade their data on the open, right? So this is actually a pet peeve that I've had with the IoT sort of ecosystem since I first got into IoT back when I was in school, is that every single device collects a lot of data. But you don't get that data, right? That's not for you. If you install a Nest temperature sensor in your house, that temperature sensor probably collects 100 data points. But you don't get any of it. You probably just get like, what temperature is it? You only get one data point, right? What's happening to all those other data points? Well, Google's collecting them, and then Google's partnering with some other company, on that data, and they're going to create some other service, and they're going to sell you that new service, right? Great, they're double dipping, triple dipping, right, on that data. The problem beyond that being very unfair is that the pace of innovation becomes very limited. My first startup was a mesh network startup back when nobody knew what Internet of Things were, right? So it was very, very, very hard to convince a customer the value of an IoT network because they didn't know what to do with the data that was collected, right? If you can't figure out what to do with the data, you think the device collecting the data is useless, right? But here's the problem, right? It's just that company thought that the data was useless. That's just one company. Right? In the entire world, did they bother asking the rest of the world whether that data is useful? No, they didn't, right? Because although it thinks that data is useless, by God, they're not going to share that useless data because, why, right? So the biggest problem here is that because devices are not opening up their data or sharing that data with the broader sort of community, the value of IoT networks, the value of hardware, is actually hugely undervalued, right? So this is like there's never really been an app store for IoT devices, right? This is the most famous IoT device in the world, right? The smartphone, right? When you're writing an app for the smartphone, do you need to know about the gyroscope? Do you need to know about the camera lens chip? You don't need to know about any of that stuff because it's all been abstracted away, right? So you can just be your software person, because all the data and APIs have been opened up to you, right? And that is how an ecosystem grows. in the vast majority of IoT today, that's not what's happening. In order to develop on IoT hardware, right, you have to understand hardware. You have to understand software. You have to have a business development team to negotiate with all the manufacturers to make sure they open up the APIs to you so that you can develop applications, right? So no wonder IoT is not growing very quickly. I know we all see these consulting reports that says IoT is growing exponentially. No, it's not growing exponentially. Okay, it's like growing at a crawl. Okay, and this is the reason. This is the reason why. Right? So if we can actually get manufacturers to provide certificate authorities, decentralized certificate authorities, and anchor them onto the blockchain, right? Now this device is an independent entity on the blockchain. It can broadcast, I am a temperature sensor manufactured by Google, right? And you can trust me that I'm a temperature sensor because Google says so, right? And then you can buy data from me. And maybe Google gets a cut of all transactions. It's a win-win. Right now everyone in the world, any developer in the world who have like money to spend, they can get access to that data, right? So that makes IoT devices much, much more useful. The other one I wanna talk about is machine-to-machine trading, right? So this one is a little far-fetched, but the one that, there's a project we're working on right now in Japan, which is a smart parking project. So we're installing these parking sensors, magnetic sensors on every single parking space, right? So that these sensors are they actually know, right, exactly when there's a car parked on top of it versus a car not parked on top of it. And it communicates with the outside world through the LoRaWAN protocol, okay? I've spoken for too long. But basically speaking, now this parking sensor, this magnetic sensor, is now endowed with an asset, right? The asset is time on top of this parking space, right? And it's actually open. It's actually able to tokenize that space and able to sell it on the open market, right? So we're not quite at machine-to-machine transactions yet. But if you think about what's coming, right? What's coming? Autonomous vehicles are coming, right? We're going to start seeing self-driving cars very, very soon. If you have self-driving cars, does it make sense for the self-driving car to go to a parking lot and then you have a guy there say, ticket, right? Like that doesn't work very well. The car should be directly transacting with the parking sensors, right? To get the best parking space at the cheapest rate. That is probably the closest machine-to-machine transaction that I see that's going to happen at mass scale very, very, very soon. And this is not a pipe dream. It's going to happen very soon. And it just so happens that parking, sucks everywhere in the world. I don't think anywhere in the world parking is great. Everyone's saying, I'm very happy with the parking in my city, right? So with dynamic pricing, with real-time bidding, right? You can get much more efficiencies into parking and make everyone's life much easier. It's not updating. That's it. That's the extent of my talk. I look forward to chatting with you guys after this. Thank you very much.